Hello and welcome back to Manifolds, the video series where we talk a lot about the integration on generalized surfaces. And indeed, in today's part 48, we go directly into the direction of Stokes' theorem. You might already know that this one connects two different integrals, and now we will look at a simple example for that. However, as always, before we start, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter, you can use the link in the description to download the additional material for the videos. So with that out of the way, I would say we can immediately start by recalling the important definition of the integration on manifolds. And one important part is that we always use an orientable manifold M. This means we choose one of the two possible orientations we can have and call it the positive one. And then the typical thing we want to integrate is just a volume form omega on the manifold. And in order to keep it simple, let's say we don't integrate over the whole manifold now, but just over one chart area U. Which just means that we can flatten the whole thing to U tilde, which is a subset in Rn. And there in Rn we have our standard orientation, which we always call positive. Hence what we want here is that the chart preserves this orientation, which means what was positive on the upper level is also positive on the lower level. And under these assumptions we have a well-defined integral of omega over u. And you already know it's just given as a standard integral in Rn. We just take the uniquely given component function of omega and integrate that over the whole domain u tilde. So in fact, we have already learned that in part 40, and afterwards we extended everything such that we got an integral for the whole manifold M. However, until now, we didn't discuss yet what happens if we take a chart which is not orientation preserving. This simply means that the orientation is flipped when we go from the upper level to the lower level. So maybe let's call this new chart K, which means this map sends a positive orientation from U into a negative orientation in Rn. And now, since the integral definition should be independent of the chosen chart, we have to introduce a sign in this definition. So this is really important to remember. We can extend the whole integral definition, but we just have to take care of the orientation. Therefore, if you flip the orientation of the whole manifold, the integral will get a sign. So usually we just have the integral of omega over m. And now by the whole setup, by the whole definition, we know that m has a chosen orientation, which we call the positive orientation. But of course, we could also flip this orientation, so we would look at m with the negative orientation. And to make this clear, I just put a minus sign here to m. And then if we don't change the volume form omega, then we already know that we introduce a minus sign in the integration. Therefore, flipping the orientation of the manifold just means that the integral gets a minus sign. So this is something you can remember for the future, because sometimes orientations get flipped. In particular, this is interesting when we talk about Riemannian manifolds with boundary. Because there we have already discussed what we mean when we look at the orientation at the boundary. Indeed, there the boundary should inherit the orientation from the original manifold M. This is something we have explicitly defined in the last video, so maybe just let's quickly recall it. Namely, a basis of the tangent space on the boundary is positively orientated if this extended basis is positively orientated on the tangent space of M. And you see, we extend this basis by putting this outward pointing unit normal vector to the front of the basis. And we know that this outward pointing is well defined. In the picture here, it's simply given by this vector. And now, since we have discussed some flipping of orientations, you see, without any effort, we can also extend this definition to the negatively orientated bases. In fact, it's exactly the same thing, we just have to flip the orientation on both sides. Now, in the case that you wonder why we write down all of these things again, it's simply because I want that they also make sense for the zero-dimensional manifolds as well. In fact, if you just consider one point, then you already have a zero-dimensional manifold. Obviously, there the tangent space is quite boring because it's just the zero-dimensional vector space. And now the only problem that we have is that the basis of the zero-dimensional vector space is simply the empty set. And for the empty set, the notion of orientation breaks down. Nevertheless, we still want to work with orientations in that case as well. So we just artificially put two possible orientations on the empty set. And we do that because in the case of a one-dimensional manifold with boundary, we need it. So for example, if you consider a curve in Rn, we have a nice one-dimensional manifold. And if we have a start and end point, we also have a boundary. So we have a zero-dimensional manifold as the boundary consisting of 2 points. And there we also want to have an orientation that is inherited from the original manifold M. So maybe let's say that these tangent vectors I put in are positively orientated on M. Then on the point Q here, we have the outward pointing normal vector there, but on the point P, we have to flip it. And this immediately tells us something about the orientation at the boundary, if you recall what we have discussed before. So for Tp del M, we have the empty set as a basis, but this one is negatively orientated if and only if the outward pointing vector is negatively orientated. So you see, this is simply the definition extended to the zero-dimensional case as well. And then the result is that we have the negative orientation at our point P. However, then on the point Q it changes because there our outward pointing normal vector is positively orientated. And there we have it. Now you know how we can extend the notion of orientations to the manifolds of zero dimension as well. And this is needed if we want to have Stokes' theorem in the general sense. And in fact, the standard Fundamental Theorem of Calculus already gives us Stokes' theorem in one dimension. And to see that, we just have to consider this interval as a one-dimensional manifold with boundary. And as we have seen before, the boundary is then a zero-dimensional manifold. So we just have 2 points, A and B, and we already know from before that the orientation should be different at the different points. Indeed, we already see that in the picture if we just sketch the interval like that. And then the outward pointing normal vector at the point B goes into a different direction than the one at point A. And obviously we would say that the positive orientation inside the interval is given when we go into the positive direction. Okay, and now we can just consider a smooth map F on this manifold given as the interval from A to B. So simply said, this is just a continuously differentiable function. And this one has a differential dfp defined on the tangent space. In that case, the tangent space is quite simple. It's just given as the one-dimensional vector space R at every point. So by definition, this is a one form that gets vectors as an input and a real number as an output. And obviously we can just identify that with the standard derivative of f written as f prime. Therefore, the nice one form on the whole manifold M, which we would write as df, can be interpreted as f prime dx, where our dx comes from the standard basis. This is quite clear because a nice chart for this manifold is just the identity map anyway. So the result here is that we immediately have a one form and we can integrate it. And please note, for the integration over the manifold M, it does not matter if we include the boundary points or exclude them. In other words, we could also say that we have a nice manifold without boundary where we can use all the results of the integration from before. In particular, as we have discussed at the beginning of the video, this abstract integration on manifolds is just defined by the concrete integration in Rn. Hence, in this case, we just have the explicit integration just in one dimension. And since we just have the identity map here, not much changes. So if you want, you can see the whole thing as an abstract manifold where we have the chart given as the identity map. Also in this sense, our f prime is the component function which we essentially integrate in the end. And exactly there we know the result already because we have the fundamental theorem of calculus in one dimension. So we have f at the point B minus f at the point A. Now integrating this one form was not a problem at all, therefore I would say let's integrate a zero form now. And indeed any smooth function like our f is a zero form by definition. And we integrate it over the zero-dimensional manifold del M, which simply means that we have two separate integrals, one over the point A and one over the point B. However, as we have already mentioned before, our point B here has a positive orientation, whereas our point A has a negative orientation. Which simply means that the first integral here will get a minus sign when we evaluate it. And evaluating zero-dimensional integrals is quite simple, because we just have to put the point into the function. Hence the first one is f of a and the second f of b. However, as already mentioned many times, the first entry f of a gets a minus sign. And with that, we immediately recognize that we get the same result as the integration of the one form. Or to put it in other words, for every smooth map f, we have this relation here on the left hand side. So the fundamental theorem of calculus can just be rewritten as the integration of a one form. And it's quite easy to remember because this d here gets pushed into the integral boundary as a del. So it's a really nice formula, and I can already tell you this is known as Stokes' theorem. And now what we will do in the next videos is to extend this result to higher dimensional manifolds and also prove it. Therefore, the first thing we need to do is to define such a d operation for n forms as well. However, this is something that needs some time, so let's do that with the next videos. So I really hope I meet you there again and have a nice day. Bye bye.